should say, have reviewed or most likely have practiced finding when a particle from particle motion is decelerating or accelerating by multiplying the velocity and acceleration together, in which we remember that negative and negative means we would be accelerating. If we had negative and positive for the velocity and acceleration, or vice versa, we would be decelerating. We will be from the calculations that we're doing today. It's going to be slightly maybe different, but we can actually just multiply them together by calculating the implicit derivative. So by multiplying the implicit derivative pieces together that I'm about to calculate, you can actually do that and put together a table, which is, if I take the implicit derivative, f prime of y, we're going to get 2y, and then y prime is going to come out of that. Let's see, what else do we get? We got minus 3, and then y prime. Now, the cool thing about when you do these is that you may have missed it. You can factor out that y prime piece. All right, so I'm going to do that here. And that's going to, if we take these two pieces, it does seem a little odd that what we get out of this is by separate explicit calculation, that inflection point, right, where it changes. We have another piece of concavity that we would have missed originally if we were just looking at f of y or y prime by itself. You pick that back up in the whole multiplication process as you've done before to see if something's accelerating or decelerating respectively. And we can see on the explicit version of the graph of f, y, and y where that's going to occur. Now, this isn't the inflection point in the traditional sense, and that's where the confusion really kind of takes root in the mind of the student. But the reality is you really are looking at all of these pieces separately, and you're really kind of combining these two different, very different, seemingly different concepts here regarding that information. And it seems a little disjointed when we're talking about it. But if you just trust the math and the analysis, it all starts to make sense. If we look at the graph, if we just look at the pieces of that, everything before -1, and we can see in our autonomous field seems to be concave down for sure. So that's going to be somewhere in here, right? We'll see these concave down, possible concave down solutions for our solution curves, correct? And we can see that if we combine our signs here before -1 respectfully, right, we're going to get the fact that if I had, like right here in my f of, or my y prime respectfully, that I'm going to have a positive value before -1, right? So I'm just going to say before -1 here for the graph, no function here. Well, the two functions respectively. So we can say that f of y or y prime is positive. And then we can see that from the line here to y minus 3, which is our second derivative, that before -1, our second derivative, notice how I say second derivative in the sense, in the sense that you are analyzing f prime of y explicitly as a first derivative, but really what's going on is that's most certainly our second derivative piece, or the acceleration. That's negative before that value, -1, and validated by the fact that when you multiply those together, the way we see it in the autonomous field is that it's concave down, or we can say that it's decelerating. It's starting to approach that equilibrium value, y equals -1, before it shifts its concavity to concave up again, which I'm about to show. So if we look at that portion, and I'll put these two together somewhere before -1 here. If we look at anything regarding, when it passes -1, you might have this piece being negative here. So you could say that after -1, that f of y prime is a negative value, right? Or negative y prime respectfully. This is just notation. And then you would say that your line here after -1, did I say that? It's after -1. I'll make sure y'all know that. That f prime of y, or y prime prime, the more important piece there, So having those two pieces of information, we know that when we multiply these together, when we're doing acceleration and velocity, because that's the comparison here, that when we do our two negatives together, when we multiply both our negative for that value and our negative for the other value, we're going to get a positive in return. If we look at the graph here and we select maybe a solution curve in that region for any appropriate initial condition, we could say that's negative 1/2. Then somewhere on the graph, we can see we might get something like this curve right here for our potential solution. That's going to be concave up. So then when we put these two pieces of information together, both graph curves are negative, giving us a concave up result. That means it's picking up speed, respectfully. You can kind of see that as maybe, where's this at? If that's -1 here, then at -1/2, it's picking up speed in the sense of how we dealt with velocity and acceleration, but in the sense of the autonomous field, more so that it's concave up in that case. So we're kind of taking what we know from velocity and acceleration and we're putting it all together. When we do the explicit calculation and the implicit calculation, and we combine them, like I'm saying in this mathematical conglomeration of a Venn diagram, just to kind of give drive the final nail into the wood here. If we look at any value past 3/2, you get something like this. We can see that in this region, specifically, we would say in this region here, that you have both positive and negative values right here, you would say, right? That's going to be concave down, um, respectfully. Maybe I didn't make that obvious before because earlier we were talking about the values before 3/2, the inflection point, which I need to make clear here that would be concave up, and then this portion would be concave down. So if I pick a -2 from what we were doing prior, that's going to give me a -4 minus 3, which is a -7. This is going to give me a -42. And we can see here that you have a positive velocity and negative acceleration. So anywhere past -2 here, we can see that was that solution curve that we had here at the bottom. And then if we pick a -1, then naturally you're going to have, what is that, a -5, right? -2, -3, so -5. But then ultimately you have this 0. That's definitely going to be our flat line, right? Where the we're finding an actual equilibrium point here. And if we do 0, but let's plug this into the function, then we should see on the graph that we've got both negative values at 0, that being looking at our graph past, well, we're at 0, we can see that most certainly is concave up, that positive value. So we can just start writing everything in here. This is going to be concave up. Down here we have the equilibrium point, and then concave down. So this would be your concavity phase line, respectfully. Entire implicit derivative here, which is quite convenient. Each one of these now gives a different interpretation. In other words, now it's focused on the concavity, not the attracting or repelling or semi-stable solutions, unstable solutions, or stable solutions, respectfully. In which I'll go into detail more if need be. So if we plug our 3/2 in, we most certainly will again get a 0 for the concavity, but that does not indicate anything in terms of a critical point dealing with the first derivative. And it makes sense when we look at the autonomous field, how kind of perplexing that can be. When we look at it, we see that there's no flat line, and we shouldn't, because right now we're doing the first derivative of the explicit, or if you will, the second derivative implicitly. In other words, this is entirely a different set of information. It regards all three. So yes, regarding all three factors, I guess you could say, or all three equilibrium points, including the inflection point. This has to deal with our concavity, not the specific equilibrium here. If we pick a 2, looking at both graphs are very useful, actually. I would highly recommend doing both. So if we look at 2 here, let's plug it in just numerically and see what happens. So you're going to get a positive 1, negative 2, and then a positive 3. Altogether, you get a negative 6. And so that tells me that my concavity at 2 before the third here, and you can barely see it, maybe at 3 really, that we're going to be concave down. We plug in 4, naturally we're going to get 0 there. That would give me my flat line for that critical point we found from the y prime of t. And if we look at this here and plug in a 5, again, that's going to give me a positive value. That's definitely going to be concave up. So again, this is the baseline dealing with your concavity. It wouldn't be the one that deals with your equilibrium points like we had dealt with just y prime of t or f of y. And so just to recap on what we just did, we were multiplying different values to find the concavity where we saw negative and positive from the explicit graphs here respectively. We then approached negative 1, which was the equilibrium point. Also, there would have been an equilibrium point in 4 prior. We were missing 3 halves before we took the implicit derivative and the explicit derivative of f of y. Anyway, as we approached or went away from negative 1, we got concave up, seeing those both being negative over here in this graph. Then we, of course, we can see that that's interpreted as the first derivative in f of y, so don't confuse that. If you took the second derivative, you would, like I said before, miss information. That's why we do the implicit derivative. Anyways, when we get past that, we can see that it starts to change from concave up to concave down again in this region. So then we can see that here, and when we multiply them, that's going to give me negative or deceleration, right? And we can see it in that way. And then if you get further along to 4, it becomes 0 again. That's an equilibrium point. And then testing 5, we got concave up, and we can see that here when we plug that. In fact, it looks like that might be an intersection anyway, or close to it. It's a little bit different. I think it would be like right here and here. Yeah. But regardless, anything past 4, naturally.
Ninja vanish!